Hi, I'm Tahiya and I'm from Rutgers University. Today I'm here to talk about our work on tracking urban heartbeat and policy compliance through vision and language-based sensing. This is a work in collaboration with Qizhen and Jorge Ortiz from Rutgers University and Ilan Mandel and Wendy from Cornell Tech. During emergency situations such as a public health crisis like a pandemic or a natural disaster, state and city governments mandate policies for crisis mitigation. However, how effective such policies are or how well the public complies with it at urban scale is hard to measure without explicit input from the public themselves. Measuring degree of compliance at urban scale can be useful as it can inform future policy design, while sensing modalities such as sound, vision, and radio frequency can be useful to sense urban life. Urban scale data in such modality need enormous processing and storage capability. So how to understand effect of public policies on urban heartbeat using big data? While location-based mobility can be used to measure compliance, they can be compromising individuals' privacy and can be detrimental to civil liberty because of constant tracking by authoritarian regimes. One way to sense policy compliance can be through images collected across the city. Public activity on the streets can be a proxy measure for urban heartbeat and policy compliance. Such street-level images can provide a street-level perspective, which can be great to understand policy compliance on city streets. In this work, we gain insights about policy compliance from a street-level perspective. To do that, we obtained licensed access to Nexar's street-level image dataset. Nexar provides instrumented dashboard cameras on ride-sharing vehicles such as Uber, Lyft, and taxis, and collects on-road images to improve road safety. Through our licensed access, we use Nexar's database of nearly 1 million images from March 2020, the start of the stay-at-home order in New York City, to September 2020, when phase 4 reopening was completed. Since we are interested in capturing human activity through semantic descriptions from images, we employ a vision-to-language model to generate semantic descriptions of image. However, to train a vision-to-language model from scratch is computationally expensive. To reduce computational overhead and label data requirement, we use transfer learning approach, where we pre-train our model using Flickr 8K dataset, which contains 40,000 image caption pairs. Our vision-to-language model contains a CNN block for encoding image features and an LSTM-based RNN block to model language features. Once our model is trained using Flickr 8K dataset, to fine-tune the pre-trained model on our own dataset, we use 1,000 examples selected from our dataset and annotate them with a caption describing the actor, action, and activities present in the image. Using this 1,000 examples label set, we fine-tune our model by training for 20 epochs. Using this fine-tuned model, we then generate captions for all the remaining images in our street-level image dataset. In our next step, we are interested in modeling the topic of the generated captions. We first pre-process the input captions to create a corpus by converting the captions to lowercase, removing punctuation, stop words, and tokenizing the documents based on their frequency. Once we obtain our text corpus, we use that as input to our topic modeling technique. In this case, we used Latent Dirichlet Allocation due to their interpretability in high dimensional space and low level requirement. In topic modeling process, optimization is performed among document topic density, topic for density, and number of topics. Once the optimization is performed and the topic model is trained, we can then compare topic distributions from different time frames. To perform this comparison between topic distributions from different time frames, we use a distance metric called Hellinger distance, which allows us to compute similarity between different topic distributions. Now let us look at some results. Here we assign each image into different time bins to capture weekly, bi-weekly, and monthly transitions over the 6 months period. Each bin is compared with all other bins using Hellinger distance and is presented as a heat map. In weekly distribution, April-May distributions are different from March and June, and also the other months, as many new policies were put into place during this time, such as face mask requirements by New York City government in April 15. On April 30, subway and school closure were announced. In biweekly distribution, mid-June to July distributions are different from earlier months, which can be attributed to the phase 1 and 2 reopening, when smaller gatherings were being allowed. In our monthly distributions, we see July-August distributions are different from earlier months, which can be attributed to phase 3 and 4 reopening, which occurred on July 6th and July 19th. This also marks the time when New York City started allowing large gatherings, which we believe reflected in the topic distribution. We also analyzed how physical mobility and visit patterns changed in the city. Here we show the number of unique visitors in restaurants and stores in the city. In April, the number dropped by 70%, but starting from May, it started to gradually increase, which is also the time when reopening started to occur. However, in the right figure, we show the categorization of the visit by visit duration. We can see that visits of all duration dropped in April, but shorter visits were increasing again by May. But number of longer visits were still quite low. We conclude that limited mobility and visit duration happened during April and May to reduce exposure to virus transmission, which later started to increase at a slow pace. One concern for image big data is often the privacy concern that can be traced back to individuals. In our analysis here, we converted the image space to language space through topic modeling. Topic model lacks individually identifiable traits as it captures urban scale phenomena without anonymization need. Another concern for our dataset is that our data is highly imbalanced across different locations. We sampled 500 images 10 times and sorted them based on their location. Here we show the average result. We see that some areas are less represented than others, with Lower Manhattan, which is the business hub of the city, with a median income of $200,000, and East Harlem with a median income of $21,000 and a Hispanic-based population being among least represented areas. This suggests that such image dataset may not reflect population from all socioeconomic status. Our validation dataset is also imbalanced across different ages, as older people are less likely to participate in public data collection process. The dataset imbalance indicates that algorithmic policymaking based on such dataset pose risks of disparate policies, and we need to find debiasing protocol for ensuring accountability and fairness. In conclusion, we present a vision language model-based approach to sense urban life and compliance level in response to public policies. We also use a unique dataset of dashboard image data for sensing in smart city. And we show that this can open up opportunities for vehicle captured images and application based on such dataset. Our analysis also show that converting the information from one space to another can enable big data-driven urban applications with lower processing and storage requirements. With that, I'm going to conclude my talk. Thank you for listening.